In the last class, what we had done, we had discussed the different aspects of crystal field theory, which the basic foundation of which was that the ligands were treated as point negative charges, and as they approach the metal atom, the metal cation, their orbitals interact, and due to the repulsion, there is increase in energy, and accordingly we draw the diagram like this. When we consider an octahedral situation where you have all these things, if considering a free metal ion, and then gradually as the ligands approach the metals ion from plus x minus x direction, plus y minus y direction, and plus z minus z direction, so 6 ligands from 6 different sides along the 6 different axes, plus minus, you have, then this is the situation. You have both the energy of both the orbitals will be raised, but T2G orbital sets of orbitals, like they are not coming in the direct line of approach, so the repulsion will be less, and so it will be lying it lower. EG set will be lying up because they are directly in the line of interaction, in the line of approach of the ligand, which are the negative charges, and the orbitals directly come head to head like that. So the repulsion is more, and that's why due to the repulsion, energy is increased to this extent. And then we consider the average increase from this situation to here. So that is the average, statistical average, which we now call as barycenter. And with respect to this, we can define that the energy has been raised by plus 0.6 del naught for the EG set, and energy has decreased for the T2G set. So your reference is important. This reference that we were talking about, and this is why I am emphasizing it again and again, because people make mistakes over this point. Okay, this is so the free metal atom situation is different, right? And directly octahedron. The other view that we had taken for the same thing to was like okay, so other view that we had taken was this, that consider a metal ion which is metal cation, which is subjected to uniformly distributed spherical negative charges which are distributed in a uniformly, just like a sphere, around the positive ion. So this will be the situation. The energy will be raised for all the 5 orbitals, but now if these charges are rearranged at the 6 corners of the octahedron, then 6 vertices of octahedron, then there will be the average energy will remain same as here, but due to individual positioning of these things, again there will be different energies to which it will, one will feel repelled, another slightly coming down. So this is the situation that emerges. So this is also a correct explanation. So these two are, so your reference point is important. Either you start from a spherical environment, spherical to octahedral field. So this is what we mean by saying that we are switching from a spherical field to an octahedral electric field, which essentially means that the distribution of charges has changed. Negative charges which were distributed over a sphere, now they are occupying the 6 vertices of the octahedron. In that situation, keeping the distance same between metal and ligands, if we arrange it this way, then there is splitting. Overall, the average energy does not change, but individual energies of the 3 sets undergoes a change. So these two pictures you can keep in mind while describing the thing. So based on this, we had discussed last class. So it is always important how you describe spherical to octahedral crystal field. The reference point is should be clear. Okay. So based on that, we had in the last class we had already discussed these things. Uh, why the colors appear. We also discussed in the last class why the effect, different factors that control the del knot, the splitting. So it was the charge on the metal, the oxidation state of the metal, and the nature of d orbitals involved. Three things for metal. And for ligands also, this was ligands. It was the series. If you fix the metal ion and then make complex with all of them and arrange them in order of increasing absorption absorption uh, energy, the del knot, which is representative of the del knot. So that is smaller to higher, you will find something like this. And so you have halides ions on the left hand side, less side, oxygen donors, then nitrogen, then carbon. So the highest one is the one with the having the carbon atoms as the donors. So all these things we had, I think the discussion we had already. So I'm just giving a recap here, and then we will move on to the where we felt that there's need for something where this theory fails. So many things was easily explained through this, as we had discussed why the color arises when there is splitting of this kind. Then if you provide substance some energy, then electron may move up and you can have the light may be absorbed, and that's why you have the colors that appear. So crystal field stabilization energy you can calculate. It is a simple thing formula, but one thing that you need to be very clear is that the when the pairing starts to begin, and that point you have to be careful. You need to compare with original degenerate set of orbitals in a free atom and how the electrons were arranged, how many pairs were there, what are the additional pairs that is being created, and then think about the pairing energy, add the pairing energy term accordingly. Okay, so this is what we had discussed, that if it is pairing energy is greater than del naught, then it will prefer to be in the higher state. Sorry, if the pairing energy is greater than del naught, then this thing will happen. If pairing energy is less and del naught is higher, then this kind of thing will emerge. Low spin complex. That. So while describing these things, what are the points that we have to consider? We have to look at these Coulombic interactions and also the nature of the orbitals 5d, 4d versus 3d. Okay, so pairing energy is much uh, larger in case of 3d, but pairing energy for 4d and 5d orbitals when you will be less. And so most of the 5d and 4d elements metal complexes are generally low spin. Besides that, we also discussed the exchange energy. For that we had extensive discussion. For the simple how I remember in the class I discussed the Hund's rule and all things. So loss of this exchange energy was a negative term which was stabilizing in nature. Okay, so if the number of exchanges decrease, number of electrons with parallel spins decrease, then it becomes difficult to pair them up. So situation like D5, Fe3 plus or Mn2 plus, they're likely to form high spin complexes because there is a huge stabilization attained through exchange energy, which may not be compensated if they are paired up. So things like you can see this in the data also. In the M2 plus divalent cation series, you'll find the maximum is here in the trivalent cation series, you will find that maximum pairing energy is for Fe3 plus. So based on these points, I also told you to note where when you are calculating CFSC, look at this 2 pi, 2 into pairing energy into 2, not 3. Why? Because if you looking at this in the degenerate case, you are having 6 electrons, 5 and 6. So there was one pair initially, and now after splitting you have 3 pairs, so there is increase of 2 pairs. That's why it is like you have to account for only 2 additional pairs that has been created. So 2 pi, why it is like this. So similarly you can also account for why this is plus, no, only one pairing energy is being considered, whereas we have 3 pairs here. So because the original situation, you will be having in a D7 system, you will be having 2 pairs initially in a not isolated metal cation. So things like this will be you have to be careful in situations like this. And also yeah, so in 3D orbitals, so we have discussed these points 4D and 5D. This 5D orbitals are more lying on outwards, they are more diffuse, and so when the ligand, the point charges are approaching, negative charges are approaching, there will be greater interaction with 5D orbitals, less with 4D, and least with the 3D. So accordingly, because of the increased interaction, there will be greater splitting, and so you have this kind of things emerging. Why this del naught is more for rhodium and iridium as compared to cobalt 3. So besides that, so this, in all these cases we had discussed, we also discussed the origin of magnetism, and then just let me go to this main point. In tetrahedral field, we also discussed that there is decrease by amount of 2 by 3, and there is no, so it's 4 by 9 factor that comes in. I told you how the 4 by 9 comes in. So it is almost like you have, so none of the ligands are approaching the orbitals head on. In the no orbital lies in the line of approach. They are only lying sideways, making certain angles. So depending on which one is making a smaller angle will be repelled more, and accordingly you will have situation that it is 54 degrees with the E2 orbitals, and another 3 set of orbitals will be making an angle of 35 degrees, so they will be repelled more. So these set of orbitals, they are repelled more, and so raised up in energy. Okay, so a factor of, so there is reduction of charge by a 2 by 3 factor, 4 by 6, remember 4 by 6, so 2 by 3 factor comes in with this. So reduction in field due to reduction in charges, then none of them is making angle uh, making a straight line, so that also causes a reduction by 2 by 3 factor, so total of 4 by 9. Okay, so the consequence is that all tetrahedral complexes are high spin. The CFS is much smaller as compared to the pairing energy. So this is the situation. Comparison has to be made from a spherical environment, and then you draw this kind of diagram. Then we had discussed the tetragonal distortion. So you can imagine the formation of square planar complexes starting from uh, octahedral one. So considering the splitting in the tetrahedral pattern, you start removing the Z ligands, removal of the Z ligands. So repulsion decreases for Z orbitals, orbitals having Z component. They will drop down in energy, and to maintain the barycenter, the XY component must be moved up. And finally, if they are completely removed, in that situation, you have it becomes square planar. So this is the situation. The Z component keeps dropping down till the Z ligand is removed. So again the Z component is dropping down in energy, and so this kind of diagram, this is for square planar, and this was the initial stages starting. This is for octahedral, this is intermediate situation, and the third one was for square planar, which is the final result of the thing. So in these cases we consider that when you have to put, if the configuration is D8 and if you have to arrange electrons, one electron in each of them, then which one should be preferred? Where should you place the electrons? If you place it like this, it will be repelled by 4, it will be repelled by 2. But if you if the it undergoes slight distortion, as we have discussed, removal of the Z ligand, Z drops down in energy, and then both the electrons are accommodated here, which will be repelled less. So this is more stabilizing in nature, and it has been found that such metals usually form square planar complexes, and very rarely octahedral will be formed. And so one example was the nickel case of nickel, in which all the three things are observed: octahedral, tetrahedral, and square planar complexes. So with a weak field ligand, it forms tetrahedral like here, and then with a strong field ligand, it forms square planar complexes when sufficient this distortion is enough. The splitting that we are looking at, del naught, it must be very high. Only then square planar complex will form, because you need to stabilize all the 8 electrons in 4 ligands. So if this is Z is dropping down in energy, it will happen strongly with a stronger ligand in case of nickel. And similar to that thing, when the ligands are not completely removed, that is the situation, you will have distorted octahedron with longer bonds along Z, and that is exactly the situation that is encountered in case of copper. So that is situation. You have D9 system, and there's a toss between what should we do, like we should put one electron in dz square, or two electrons in dx square minus y square, or vice versa. So again in this case, that consideration, so either things are repelled by 2 ligands or 4 ligands. So which one would be better situation? So usually it turns out that Z will be if you place one electron in the Z, sorry, 2 electrons here uh, in dz square, that is better situation, and this kind of effect will be found to be there whenever there is such kind asymmetric filling of the whenever there is asymmetric filling of the these orbitals. Something is repelled more than the other. One situation there is greater repulsion, other there is less repulsion due to the ligands, then it will result in a distorted octahedron, either elongation of Z. Z elongation is the more common one that has been found, or there's another way we can. So the Z elongation is this one, when the Z drops down. Earlier we discussed the case of square planar, the halfway mark in between the two. So that was the situation of this. And the other thing is that it might also undergo this kind of situation, which is rarely observed, where Z is compressed and the two short and long four long bonds are obtained. So this was the situation that we discussed with several examples. You can see, look for yourself, try to find out. You'll find that the CRF3 is the example for the four long bonds in the reverse case. Rest others are examples of uh, copper having four short bonds, two long bonds along Z. So Z elongation is the commonly observed. So what we found, that limitation was there. CFT could not explain why CO acts as a stronger ligand as compared to Cn minus, and that we will discuss today, how the metals are stabilized in low oxidation states. Okay, so those things we will discuss. So this was discussed only when we realized that uh, these ligands are not just point negative charges, they are actually uh, having their own orbitals. They are, and that orbitals can interact with the metal orbitals. So in that case, there will be overlap of orbitals, which is a covalent bond situation, and that's we need to consider. So donation of electron has to be considered, like formation of sigma bond when the filled orbital overlaps along the internuclear axis, and then sideways overlap between the filled metal orbital with the vacant pi star orbital on the carbon. That can happen. So in this way, the buildup, जो मेटल पे नेगेटिव चार्जेस का बिल्डअप हो रहा था, वो कम हो जाता है. The metal is able to shift the electron density towards the metals are electropositive. ठीक है, और उनके ऊपर नेगेटिव चार्ज का इतना सारा छः लिगेंड है, सभी इलेक्ट्रॉन दे रहे हैं. So there will be huge buildup of the negative charges, and that negative charge must be taken care of. Then only you can explain the low oxidation state in that case. So that is possible if the filled metal orbitals overlap with the vacant orbitals, that is of the carbonyl, and then there's so that pi bond formation is the bond is formed in which metal donates electron to the ligand, and so the electron density is now shifting away from the metal side, and that's how the things are stabilized. So you can see even up to -2 oxidation state of -2 can be achieved if a good mechanism of this exists. So we will discussing more on this now. So we are here to discuss that scheme of so let's look at it from the why we so how we can explain these things when we apply the molecular orbital theory, the thing that you have already learned in case of simple atoms and molecules formed by simple combination of atoms. The same thing we are going to use here. It's a bit a combination. So CFT, the thing with that, crystal field theory was able to explain many things, and here we are just adding the point that instead of everything is fine, but these negative charges, they are not point charges, the ligands are not point charges, and the orbitals, they have orbitals with electrons filled and unfilled, both kind of situations. So the overlap will happen when they come closer to each other with the metal ion, and that will give rise to things. So Ligand field theory combines the the elements of crystal field theory with the molecular orbital theory, and then we are applying it to the system, to the complexes. So molecular orbital theory, molecular orbitals that could be formed in octahedral uh, this framework, octahedral metal ligand framework. So we have to apply, look at the, again you will have to look at the possible ligands, the orbitals of the ligands, make a group of them, group orbitals, and then identify which one is having the right kind of symmetry to overlap with the metal ligands. So so donors, most of the time the ligands have p orbitals, uh, which approach the metal ion to form a sigma bond. Then on the metal side you have dxz dyz orbitals, which are not aligned, lying on along the internuclear axis. So but the other set of orbitals like dx square minus y square dz square px py pz, they are also aligned along three different axes, plus x plus y. So ligands are approaching along that direction. So px py pz, dx square minus z square, and s orbitals all have right kind of symmetry to form the first sigma bonds, okay, with this approaching ligands. So these are the orbitals that we need to consider for pz, dz square, and dx square minus y square, and px py pz orbitals of the on the metal. So all these are suitable for formation of uh, sigma bond. They can interact with the ligands. Just a moment. So so we again go to the basics of the group theory to identify the orbitals suitable, find the matching set of orbital ligand group orbitals. So remember, in just like we had done in case of BeH2, we had we have put beryllium on one side and then made ligand group orbitals for hydrogen, combining the hydrogen atoms. Now using the group theory, we will doing the same thing with six. There are six ligand, ML6 type thing is there. So you have to make like identify all the orbitals, suitable orbitals on metal. Identify the suitable orbitals, keeping the geometry in mind, and then which one are overlapping along the internuclear axis. So those will be used for formation of sigma bonds. So if you try to find that, if you apply the group theory concepts, and we will arrive finally that the representation, six ligand orbitals that are formed, they they can combine with the metal orbitals. Their reducible representation turns out to be this A1G, T1U, EG. So these are the, usually think of p orbitals on six ligands atoms, and then you will arrive at this kind of thing when you treat them according to the apply symmetry operations of the octahedral set, and then you will find that when you break down to the reducible representation, A1G, T1U, EG. Now if you look at the geometry and find the suitable orbitals on metals, you have dxy, dxz, dyz orbitals having T2G symmetry. So on bonding metals, metal orbitals, you have A1G with the s orbital, px, py, pz have T1U, and dx x square minus y square z square have EG symmetry. So these are the first few orbitals which are required for the formation of sigma orbitals. Okay, so accordingly we can start making the MO diagram. So you have metal on here, metal cation with 3D, 4s, 4p. So according to the, so now you know through the with the gift theory EG and T2G, there are two types of orbitals in the octahedral symmetry. If we consider on the ligand side, look at the ligand side, six ligand orbitals, 1 2 3 4 5 6. T1U 3 triply degenerate, doubly degenerate, EG. Whenever the symbol is T, it is triply degenerate. U and G, then these are the things that we have to consider in group theory, so based on symmetry with respect to point or reflection. So these are six ligand orbitals. 6 ligand group orbitals, right? And then you start making the MO diagram for mx6. So start match if you can. So A1G, EG and T1U. So 3 plus 2 plus 1. 3, 2, 1. 6 here. You have 6 over here. So now you start matching this proper symmetry. A1G overlapping with A1G here. 4s orbital here. So this is the perfect first set of molecular orbital is formed, and the corresponding anti-bonding is shown over here, sigma star, right? Sigma and sigma star, first sigma orbital is formed like this. Then you look for the other one, the p. So this is the usually the p degenerate set, px py, and so when they represent the eg set. Eg symmetry is you have with the dx square minus y square and dz square, so they overlap, and you have here's eg, and corresponding you will have eg star anti-bonding for that. For the other set of orbitals, so T1U orbitals, it is the 4p orbitals which is having the right kind of symmetry on this metal, which can combine with T1U symmetry of this orbitals having T1U symmetry. And so this is a third set of sigma orbitals that is formed in ML6, right? So 3 plus 2 plus 1, 6 sigma orbitals, corresponding sigma star orbitals are also formed. Now in this case, how do we define the delta naught? What we found here, T2G, there is no, for the T2G set on metal, there is nothing which on the ligand group orbitals which is having suitable match. There is no matching of, so for T2G, no counterpart on ligand group orbitals, LGO ligand group orbitals. So it remains non-bonding in nature, so it remains non-bonding. And so this difference between the T2G and EG star is what you know as delta naught. So this is your delta naught. In an MO diagram, we have only considered the sigma bonding between this metal with the 6 ligands which are arranged around occupying the vertices, 6 vertices of the octahedron. So this is what has happened. 6 metal atomic orbitals of proper symmetry combined with 6 ligand group orbitals. Metal atomic orbitals, 6 metal orbitals. So how they are combining? You just got the idea. EG set of 3D orbitals combining to give you this thing, but even 4s and 4p are participating and combining with, they also have right kind of symmetry to combine with ligand group orbitals, and the combination results in this kind of things. Now 6 bonding metal orbitals are filled by the ligand group. So if you have electron pairs on the ligands, so this is how the situation is like this. All of them are donated to this sigma bonds orbitals that you are seeing. They occupy these orbitals. Okay. Then the metal T2G orbitals are non-bonding. We just discussed. There is no counterpart of right symmetry on the in the ligand group orbital set. 6 anti-bonding orbitals are formed. So you can see Eg star as then you have. So it is the difference between T2G and Eg star that gives you del naught. Okay. And 6 anti-bonding orbitals are formed. So of course, if 6 bonding orbitals have been formed, 6 anti-bonding will also be formed. That's what we have seen here. 3 2 3 1 and 2. The two Eg star or antibonding orbitals are lowest energy antibonding orbitals available. Antibonding orbital of lowest energy is this one. WD generates it, and d electrons from the metal ion will fill in the T2G and Eg star orbitals. So we have so this is the scheme that we have for metal ligand complex ML6 type, okay, in a molecular orbital picture. And so all octahedral metal complexes will have the same MO diagram, and we will see the variation in number of d electrons. 6 bonding molecular orbitals with lowered energy. So it is the key. All ML6 type molecules complexes will have 6 electron pairs in lower energy orbitals as compared to initial situation of 6 separated ligands and separated metal. So in comparison to that, there is energy is lowered, and that's why you have this kind of thing happening. So d electrons in the T2G Eg star. So it is a comparison of T2G with the Eg star, the antibonding first lowest antibonding orbital, which gives you the strength of this thing, the Ligand field. So now instead of crystal field, we are using the word Ligand field, visualizing that the ligand is in true sense is atom or a molecule with orbitals in it, and which is able to overlap with the metals, right? Determine the geometry. So this is the crucial T2G and Eg star of molecular orbital diagram. So these are the determining the many things of the metals, properties of the metals. Orbital splitting, and we denote it by delta octahedral. This delta octahedral. So now in this context, how we define the strong field? Strong field ligands are ligands whose orbitals interact strongly with the metal ions. Strong interaction, good interaction with the metal ions, orbitals on the metal ions, and the ligand orbitals. So if they are having good interaction, as you have learnt in the covalent bonding, if the two orbitals energy is matched, they will have good interaction, and the lowering of energy will be more. We have learned this in covalent bonding. So same thing, if we are talking about good interaction, energy of the metal orbitals, energy of the ligand filament ligand orbitals are suitably matched, they are closer to each other, there will be good interaction, good overlap between the orbitals, and the bonding orbital will be much lower in energy. So such situation we call it strong field ligand. Eg star. So if there is lowering of the bonding orbital, that means Eg star, the anti-bonding orbital, will also move up much higher in energy, and delta naught will be large. Now in a similar way, we can define the weak field interactions. Weak field ligands means the ligands whose orbitals interact weakly, that is the overlap is not good, or you can say the energy mismatch between the combining orbitals are much more. So energy mismatch between the orbitals, poor overlap, less lowering of energy, and correspondingly the Eg star will be raised only slightly in energy, and this will give you a lower delta naught. So these are the things that we consider, and delta naught is small. Okay, so the electron spins will have similar thing that we have discussed in CFT. If you have understood those points, there's nothing much to discuss over here. Possible arrangement: D0 to D3, D10 to D8 to D10, only one possible arrangement, but D4 to D7 you can have two possible arrangements, high spin or low spin. So that we have already discussed with CFT, and there is nothing different. The same element of CFT is contained here. There is nothing new thing here to be discussed. So now pairing energy, that also we have discussed at length, and that is having the same consideration over here. Pairing energy is represented by capital Pi or sometimes capital P. Simply we write it, whether it's Greek or uh, Roman letters, it is the same. So Greek alphabet or English alphabet, you can use anything for representing the pairing energy. Okay, delta octahedral energy gained by, so this is what we have already defined, strong feeling high. So this is the summary that we are having here. So aqua complexes, this is the situation for the energy. So remember, whenever you have in laboratory, you never encountered a free isolated ion. You are making a solution of cobalt in the lab. Essentially, when you dissolve it in water, it is the water molecules which act as ligands and form Ml6 type complex. So you start with an aqua complex always, and then you have proceed with any other reaction. So in laboratory situation, you always have aqua complex of that is water molecules bound to metals as ligands, and then you del naught can be calculated for them for different divalent ions and trivalent ions, you can see, and their pairing energy. So this has the same concentration as we have discussed earlier. uh, the trends that we have seen earlier also, 3 plus ion del naught is higher as compared to 2 plus ion. So again, now you can in terms of metal Ligand field theory also you can discuss. Now we are talking about better interaction, because the metal ion, when is having a greater charge, 3 plus charge, it will attract the ligands much strongly, and when the ligand atom approaches comes so close to each other, the overlap of orbitals is also good, and due to the greater interaction you will have the energy levels will uh, bonding orbitals will be stabilized, anti-bonding Eg star will be destabilized to the same extent. So that's why you have this kind of situation. Third row and second row and first row metal ions, so you have this kind of, so that is we have also discussed 4D and 5D over orbitals which are lying outwards, which will have greater interaction with the ligand orbitals, and so there will be. And also there is the other thing that we notice is that in 4D and 5D the pairing energy decreases much more. Pairing, so the complexes are essentially low spin. Okay, so this stabilization, that overall stabilization that we get is called Ligand field stabilization energy, similar to what essentially same as CFSC. Although we have seen the theoretical approach is different, now we are looking at T2G and Eg star, the anti-bonding orbital, the difference between them and how many electrons are being put up in that. T2G orbitals as stabilized by this, and Eg star orbital, the one that we have shown. Okay, so that way we are able to arrive at the stabilization energy, Ligand field stabilization energy for different. So essentially you try and find out that your calculation matches with the table shown over here in case of a weak field and in case of a strong field arrangement. Try work out all these details with pen and paper on your in your copies. This is important. Okay, and the importance of Ligand field stabilization can be understood when we analyze the hydration energy of all the ions, transition metal ions with different number of d electrons. So number of d electrons on the has been plotted on the x-axis, and the energy of hydration enthalpy is on this. So you can see here this black dots is the line that you expect based on simple calculation. In absence of Ligand field stabilization energy, this is a line that would have been followed, a straight line going downwards, because energy becoming more and more negative because of the small decreasing size of the ion. But you get two humps in actual thing, experimental. These are the experimental mental thing. You get two humps here. This is theoretical. Considering there is no LFSC, without having LFSC, just an ion dipole kind of interaction would give you this kind of thing. So this is simple, considering simple ion dipole interaction between water and okay, so that will give you this kind of line. Okay, but experimentally, what we have been what is found, that there is a region where the line deviates, and that deviation is due to when you calculate the CFSC for a D2 and D3 system. You can see here for yourself in case of so CFSC, if you look at this LFSC minus 2.5 2 by 5 minus 4 by 5. For D3 system you have calculated minus 6 by 5. High value of this uh, greater, more negative on this side, greater lowering. Then at D5 system you have the LFSC is 0, so there is no additional thing, but after that again it varies, and you can see it minus 2 by 5, 4 by 5, minus 6 by 5. Again for D8 it is more negative, so greater lowering of energy. So additional lowering of energy is accounted for when you look at the D3 system and D8 system, D8 D9 system. So these are due to, so this is the experimental proof of Ligand field stabilization energy exists, and these are the effects which is obtained when you dissolve this salt. Take a transition metal, dissolve in water, you'll find this kind of thing happening. So this is the series for D3 plus ions, plus 3 charge. In all of them, D3 situation is having different like this. Okay, so this kind of graph can be obtained. Enthalpies become more negative, favorable left to right on periodic table. And so in case of simple ion dipole interaction, it should having a smooth straight line, black dots, and the open circles that you see is when you consider the double hump, the LFSC is considered, the double hump is observed, which matches with the experimental results. So LFSCs can be used for high spin or low spin, for prediction of high spin or low spin complexes, explanation of electronic spectrum, and as well as magnetic behavior. So this was a complete in itself. So Ligand field theory gives you all the aspects are considered here, and the major point that we are yet to discuss is the thing that why carbon based ligands appear to the higher side. सॉरी सो अभी अभी हमारा जो मेन पॉइंट है वो अभी बाकी है कि हाउ डू Cn minus Co carbonyl they appear on the higher side of the spectrochemical series. Why the splitting, del not splitting is more, and that is so far in the molecular orbital diagram what we have considered is only the sigma bonding between ligands and metal. Now if we consider the pi bonding aspect, then we would be able to answer the other things that we have just been asking ourselves. Um, we have only looked at the sigma interactions so far, and now we can also think of that some of these ligands can also interact, can also have interaction of their orbitals if they are available of suitable energy, orbitals of suitable energy are available, then sideways overlap can be possible and pi bonding may result. So in such cases there will be additional energy lowering, which we will be considering now, how we will arrive at that. So the orbitals used are the other p orbitals or hybrid orbitals, molecular orbital from ligands having pi symmetry. And so usually you have like in CO it is a pi star orbital. So we'll again look for the symmetry that can have sideways overlap, not aligned along the internuclear axis, but they are overlapping sideways. So we have group orbitals we choose with respect to the consideration of pi bonding, and we look at the geometry. So x, y, z like this. So px, py, pz orbitals on the ligand, you can consider them. So choose x, y, z axis so that y points directly at metal. This one is sigma. Find the reducible representation, and then so you'll have 12 px and pz orbitals. So 6 into why 12? Why not? So are you able to get it? This is the metal. Y orbital is in the line with this thing, internuclear axis. So this one will be for sigma bonding, used up for sigma bonding, right? But x and y for this particular, x and z for this particular ligand are lying perpendicular to the internuclear axis. So those orbitals px and pz will be used for this kind of bonding. So in each of these orbitals we will having situations like that, and so there will be 12 such things. Okay, so in each ligand will be having two p orbitals which have not yet been used. एक ही p ऑर्बिटल, हर एक लिगेंड का एक ही p ऑर्बिटल सिग्मा बॉन्डिंग में गया है, बाकी के दो ऑर्बिटल बाकी हैं. So they can be used for making this pi bonds. Pi overlap is possible. So now take this set of 12 px and pz orbitals and apply all the symmetry operations. Make a matrix, reduce it. So when you reduce it, do not make matrices, just apply the shortcuts as I told you in group theory to observe the things, and then reduce it further to irreducible representation. So this is what people obtain when you consider this. This is the representation characters of that, and then which can be further reduced to T1g, T2g, T1u, T2u. So this is the ligand group orbitals, which an intense rigorous group theory treatment gives you this kind of thing, that orbitals which are on ligands which are suitable for overlapping with metals uh, to in a sideways manner. So what we find here, that if we have, when we consider the 12 px and pz sorry py orbitals, pz orbitals, we find that only the set which is having T2g, this is for ligand group orbitals, LGO, this one is having matches very well with the symmetry of on metal, T2g orbitals on metals. So this combination will be overlapping well, and T1u, which appears here, matches with the px, py, pz orbitals for pi bonding. So this kind of thing can happen. Okay, look at this representative orbitals on the metal and the ligands. So dyz, yz orbitals are considered here. On the ligand side, you have dyz of the ligand if the ligand possesses d orbitals of the suitable pi star orbitals. They can also overlap. So see how sideways overlap can result. So this is a pi star orbital. So imagine CO type ligand can overlap, and then you have also like Cl minus type overlap. So this kind of three different types of ligand orbitals exist which can overlap with the metal d orbital. So taking one example, it has been shown. Now, so this is the example of cyanide Cn minus. So this is a MO diagram of Cn minus. So what is MO diagram for Cn minus, Cn, and in the middle you have Cn minus. So in this case you have highest occupied molecular orbital, and this is the lowest unoccupied molecular orbital pi star suitable geometry. So this is the case that we are discussing. Dy with respect to dyz, this matching, this kind of thing can take place. So a sigma bond will be formed when this particular molecular orbital overlaps with the vacant. So this kind of thing can happen. So this particular filled orbital, this will be for these electrons, sigma electrons, will be used to donate to metal ion. This pair will be, and lowest unoccupied orbital that we are seeing here will be used for accepting electrons from the metal ions if suitable orbitals are available on the metal with filled electrons. So the pi star orbitals are higher in energy than the metal T2G star. Orbitals pi star, this energy is having higher energy as compared to the metal T2G star and have correct symmetry to overlap with them. So now we will be constructing another diagram in which Cn minus will be acting as ligand. This is the MO diagram for Cn minus. Now take this thing with these two things, the HOMO and LUMO. Take this HOMO LUMO and now make it overlap with the metal ions. So pi bonding will result when you have, this is your sorry, this is the thing. So this is your metal and this is the ligands. So now we are moving from the previous MO diagram which considered only overlap of sigma bond formation. So with sigma bonds only, ligand ML complex was something like this. ML complex with sigma bond only was like this. T2G and EG star was there, right? And this we consider as delta naught. Now when we are taking this empty ligand, sorry, this is empty ligand is on this side, ligand is here. So empty ligand having T2G symmetry, then these three dxy, dxz, these orbitals have right kind of symmetry to match with, and their overlap happens, resulting in the formation of this kind. So this is a sideways overlap that is happening. Pi bonding is, so pi, so if the ligand orbitals are empty, metal orbitals are filled, T2G set, which was essentially non-bonding in case of previous picture. When we consider sigma bonding, T2G set was non-bonding. It was not having right kind of match with the other orbitals. But now if the orbitals are present on ligands which have T2G symmetry, as in this case, in case of Cn minus, in case of CO, then this overlap is further possible, and with these filled metal orbitals are now coming into over here. So this lowering, so this T2G set is now further lowered in terms of energy, and delta naught Eg star remains in the same place, and delta naught, consider delta naught increased. So this is how you can you are able to explain how the delta naught goes high for such systems where pi bond formation can happen. The metal orbitals are T2G orbitals in metals are full. T2G orbital in the Ligand group set is empty. If the overlap happens, then the 3 electrons go into the pi bonding molecular orbital. And if we now consider this difference between T2G, so there is lowering of energy due to pi bond formation, and T2G to Eg star distance, gap increases, and so delta naught increases. Okay, so this is the kind of situation that we see in CO and Cn minus, and we call them a strong field ligand. Okay, so this is what we also know as metal to pi back bonding, the overlap pi-acceptor. So metal has filled orbitals, T2G set is filled with electrons, and ligands are vacant. So this is donation of electron to the empty ligand group orbitals, and this is what we know as pi-acceptor ligands. Okay, whenever you have this kind of situation, the delta naught will increase, which is now perfectly explained by molecular orbital theory. Okay, so this transfer of electron density away from metal M plus stabilizes the complex, as compared to a sigma bonding only situation. This bonding situation now improves the overall stability. Now there could be a second type example, which we should also consider. Suppose the ligand group orbitals filled. If they are filled, reverse situation, when the ligand group orbitals are filled already, and you have a T2G set on the ligand which is filled. In previous case, we have considered ligand group set T2G set were empty. If they are filled, the T2G set here in the Ml6 complex with sigma bonds only, that situation we had already discussed in previous diagram. So from that diagram, if we now compare, so now again consider the overlapping of T2G set with this, then 6 electrons from this filled group orbital, they occupy this position, and the 3 electrons now are going to occupy the T2G star anti-bonding orbital, and the gap is now this one. Delta naught is given by the difference between T2G. So delta naught has decreased. So what you see here, delta naught decreases because now these 3 electrons have no place to occupy but to occupy this anti-bonding T2G star orbital, and the difference between the top filled orbital and the first unfilled in this molecular complex will be your delta naught. So that gap is now reduced. So this kind of situation, so this happens in fluorine F minus ions. So that is acting as this kind of situation is for what we know as pi donor ligands. So F minus is a pi donor ligand, and in that case delta naught is much less because of this reason. Okay, the scheme of bonding that we have just shown. And so the filled p orbitals are lower in energy than the metal T2G set. Here look at the positioning of the things. Ligand group orbitals are lying lower in energy as compared to the metal set, and then this is the situation that arises. In the previous case, when we have considered Cn minus or Co, the T2G set on this thing was, this was lying much here. Empty ligand orbital, ligand set was lying above the metal. This was the metal, and metal in the metal ligand complex, T2G was non-bonding and it was lying lower in energy. Here in the second case, what we have seen here, the metal T2G is lying above the energy of T2G in the ligand group set. And it also, so there are two things that has changed. The ligand group orbital T2G set has filled electrons. It has 6 electron pairs. It is also lying lower as compared to this. Earlier the metal T2G set was lying lower in energy, and because of this, when we consider the MO diagram, this goes slightly, the 3 electrons in the metal T2G are now occupying the anti-bonding T2G star orbital, and the difference between the two is now less. So this is how, so two type of pi bonding situation we have discussed: pi acceptor and pi donor. This one is what we know as pi donor, which is with fluorine. This kind of situation is encountered, okay, and delta naught is decreased. So unexpectedly F minus is very gives a much smaller delta naught value, and this is ligand to metal pi bonding. This is a ligand to metal donor. So FCl H2O, these are weak field due to this reason, and they favor, so the both the things situations are combined into one, which is shown over here. So Ml6 with sigma bond metal, ligand 6 with sigma bond complex. So basically it is the T2G Eg star with and then the two situation, the filled ligand group orbital here lying lower in energy, empty ligand group orbital lying above in energy. Two different situations, both so we have combined the two pictures, and so increase in del naught, look at this, increase in del naught, decrease in del naught. So you have increase and decrease in del naught situation depending on how the T2G is in the ligand group set is lying in energy, how low or how high as compared to the T2G on metal, and then whether all the electrons are filled here. Here it is empty, vacant. Okay, so pi acceptor, this is pi donor. Okay, all the things summarized in one diagram. Okay, so that's all for this, and I'll meet you tomorrow morning 7 a.m. We have to complete this